Hello all, welcome to this PTX series videos where we get to try our hands-on with the Renesas NFC solutions. You may already be familiar with the PTX105R IoT module, which is a small footprint NFC reader and host card emulator suitable for extremely portable applications. Renesas provides a SDK that can be compiled directly for ARM Cortex MCUs and also comes with an example project ready to go. In this video, we are going to compile and run that example project. This example project provides a blueprint for IoT applications showing the appropriate use of different APIs associated with the PTX module. As primary functionality, the example project has card reader as well as host card emulation. Developers can also choose to enable different NFC protocols, making the application compatible with various types of cards. The application contains functions to handle different NFC protocols and can be used to detect different types of cards. It also contains the API implementations specific to the NFC operations and shows example of how they need to be used with applications. As we scroll down, we will see that the definition for different card protocols are provided as switch case statements, allowing the use of different data processing methods for the type of detected cards. To start, we shall launch the primary development tool from Renesas, the E2 Studio, which is an Eclipse-based IDE. We shall import the example project through the SDK. Once imported successfully, the project contents will be shown in the Explorer. We can open the configuration.xml file to see the project components. The various stacks are already included and configured for communications, debugging, timers, etc. We shall soon notice that the default board on which this SDK is based on is the EK RA4M2, which is a Cortex M33 MCU. Now, for our demo, we have another CM33 MCU board, the EK RA6M4. We can change our board type from the BSP tab. This will load the configuration for the board of our choice. Once the configuration has been altered, we shall notice one of the stacks, the USB-P CDC, is showing some error. By hovering over the iLink, we are told that the USB clock configurations need to be changed for this new board. So let's look into it. This step involves some minor configuration changes to suit the SDK to our board. As per the current error, we need to navigate to the Clocks tab. We need to set the USB clock or UCLK to 48 Hz. In order to do that, we need to enable the USB clock and set PLL2 as the source. Then we need to change the number of divisions and multiplier variables to obtain the desired frequency of 48 MHz. This would eliminate the error that we have been seeing. The other possible configuration change needs to be with assigning the correct pins to the PMOD2 stack. Now, the PMOD2 port is hardwired to specific pins on the board. So, we need to make sure those pins are correctly assigned for this new board, since the default SDK is made based on the pin configuration of the RA4M2. By comparing, we can see that the mapping for the essential pins, that is, the transfer and interrupt pins, is identical between the RA4M2 and RA6M4, so there is no need to change any of it. We will just make sure that the pins have been assigned without any conflicts. We will also check the transfer and receive pins for the EWART port that is designated as debug. we note down the pins 112 and 113. This will be used to connect to the PC terminal. We also note down the set baud rate. We can press the Generate Project Contents to generate the RA6M4 specific configuration files for referencing in the project and also overwriting any previous configurations for RA4M2. Next, we will build and debug this project. Before we debug the application, we need to make sure the PTX module is plugged into the PMOD port. If the PTX module is not plugged in, the application will run into an error and halt. We will also connect a USB to TTL converter to the pin P112 and P113 of the board. The pin 112 connects to the RX of the adapter and pin 113 connects to the TX of the adapter. Now we can click on Build to compile the project contents into the executable application. Okay, there seems to be an error. More specifically, some multiple definitions. We can identify the concerned files by the small red cross mark. Seems like there is an error in the debug port file. Okay, there are two files. One of them needs to be excluded from compilation. We shall right-click on the ORI file and exclude from build. Let's recompile. Alright, seems to have gone through fine. Next, we shall upload the application to our device. We will find the Renesas GDB hardware debugging option, which is at number 4. When asked, we will agree to switch the perspective. We will press the resume button on the top bar when available. We shall press again until the program starts running and shows status in the bottom left of the screen. Now, we need to open the TerraTerm terminal to monitor the console messages as we run the application. We need to set the COM port, which will refer to the USB adapter we are using, and then we need to set the baud rate of the serial port. If no text appears on the screen, you can press the reset button on your board, and we can see the messages in the console from the start of the application. The last line says waiting for discovered cards. So I will place an access card to see if we get anything on the screen. And there you go. Every time I'm scanning the card, there are messages being exchanged between the card and the NFC module. So this example application will essentially allow us to run the PTX out of the box and allows exchanging and capturing data. And that's all we have got for today. See you in the next video.